nanometers, quantum mechanical effects, quantum effects are prevailing, and the classical dynamics are completely failing at that interactions. And so people started, they cannot further reduce the size of the silicon interactions, or otherwise the chip design manufacturers were unable to further reduce the size of the silicon. So they started thinking of new dynamics, and they started searching for, yes, what is this? Can we use these quantum principles for information and all, right? The attribution of information towards quantum is completely different. And if you see in the world, there are various quantum technologies, various different quantum technologies which are governing the quantum computing principles. Some, if you see, if you go to the Google and ask, definitely n number of PPTs, n number of videos you will be getting saying that quantum computing you can do with superconducting material. Some people say it is measure on tiny particles. Some people say it is spin state, spintronics of an electron. And some people say it is new technology. Even Microsoft has come out with a very new technology, right? Some people say that quantum computers are built with the trapped ion. And there are some other quantum computers which work with annealing technologies, quantum annealing, we call this as quantum annealing. Maybe like, all these terms seems to be very much available in the internet, but you will be getting confused. I don't go into depth of any of these technologies. I'll just briefly give you the introduction of what is, why you should be learning this quantum computing technology. You should be learning because, see, as a faculty, more than a student, there is a lot of learning curve for the faculty. Until he leaves his retirement, there should be a learning curve. And this quantum computing will be the next upcoming field in nearly 5 to 10 years. It is not completely perfect right now as of our concrete silicon technology for electronics and all. Normal computing, we have got complete concrete technologies which are there for normal computing. We'll call that as normal computing as classical computing. This quantum computing is totally a different way of attributing information. It cannot be same. See, classical computing attributing information is different, quantum computing attributing of information is different. So for example, if you say you have got, say if I take a keyboard like this, 4 switches are there. If I press some keys, press it is 1. If it is not pressed, we acknowledge it is 0. A set of such switches we attribute to some information. That kind of switch on or off, we call it a transistor switch on or off in our electronic circuitry, we attribute as one set of, say, 4 bits together, we call it the nibble, and 8 bits as the byte, and a word maybe of 8 bits or 16 bits or 32 bits or 64, 128, now it is 256. That we call it as a one word. Even you take 1 bit of information or processing is done at that complete one word. Every event is triggered by a clock. If you see a conventional classical computing system, every event is triggered by a clock. Unless there is a clock, there is no action taken by the computer. So for example, if I am standing here, if I am a classical computer, I will not talk continuously. Unless there is an event, some trigger. Unless there is a trigger, when the triggering is there, events happen. That means the states get changed. Unless there is a state change, you cannot have the information flow from one part to another part. The computation is also like that, right? In that manner, I can say these classical computers are a kind of serial computation, one after the other. Sir, we have got parallel computers which are available right now. When parallel computers or supercomputers are available, how can you say that they are serial computations? See, all these parallelizable independent tasks are given to different processors together on a different processors, and they are togetherly executed in such a way that you are getting parallel execution, but on a whole we can say it is a serial computation. But whereas if you see this quantum computing, it is not like that. It is completely parallel computing by virtue of the quantum mechanical principles. And what is meant by quantum computing? The computation done with the help of quantum mechanical principles like superposition, interference, these are the majorly two fundamental principles: superposition, interference. What else? These are the two fundamental principles which are governing for that parallelism. There. And there are basically two different algorithms which fascinated people to run around this quantum computing. One such algorithm which made people to invest is Shor's algorithm. Shor's. With that, he gave a theoretical interpretation with a proof saying that using this quantum computing, you can get the prime factors within fractions of time. Prime factors. See, you know the prime number? When you try to multiply two prime numbers, it will give you a large number. Again, it is a prime? I don't know. Because these two are factors, no, it is not prime. But to find the factors of that product of two prime numbers, it is not an easy task for a normal computer. Even if you take a highly super fast supercomputer today, it takes a lot of time, lot of computation time, say years together. But with quantum computer, they say it is at one go. It is all with one go, you will be getting the prime factors. Right? That is Shor's algorithm, which made people to fascinate, think and look about, yes, we require quantum computers, and we start to invest our time and money towards quantum computers, and the investors started investing money, and that is how the research community or scientists or the faculties in the university started their efforts towards quantum. These quantum principles were there long back, and who is the Feynman is called as the father of quantum computers. He is the first person who started to make people think, why don't we try to simulate physics with computers? Simulating physics of particles with computers is nothing but application towards implementing the quantum computing. Right? I'll go and I'll just brief out my presentation with the slides which I have got, and we will be having an interactive session rather than sitting one way dialogue. Because by the time you come here, you would have known by the news saying that quantum computers can do that thing, quantum computers can do this thing, and they are the next generation computers. No doubt they are next generation computers which are going to come, right? The information processing with quantum computers is totally a new method. It is not like a conventional method. We make equivalence of conventional method and we try to process for our understanding, but the method of processing the information is completely different, a new method. In our classical computers, as I have told, the information is at a state either 0 or 1. So, for example, if you see a switchboard and say 4 switches are there, until nobody else is going to trigger the switches, you don't find the switches are getting changed. So, for example, if I say there is a switchboard like this, I assume that there is a switchboard and 4 switches are there. Some 2 switches in between I switched on and other 2 are off. Say 0, 1, 0, 1. Right? This state we attribute as information as 5, 0, 1, 0. Right? But quantum computer, the state of a qubit is not fixed to either 0 or 1. It is between 0 and 1. It is not just 0 or 1, it is in between 0 and 1. Or 0 and 1 also. It is a both. We call that state of a quantum state as a qubit, which stores the information as 0 or 1. Right? The beauty of this quantum qubit is that the state between 0 and 1, so for example 0.5 of 0 and 0.5 of 1 can also be attributed to some other information. 0.75 of 0, 0.25 of 1 can be attributed to another kind of information. With a single qubit, lot more of information can be attributed. When you are able to attribute lot more of information, that means it has got a capacity to store large amount of information in a single qubit. Right? It is not single qubit. If I say there is another qubit, if more qubits are used, that is an advanced topic, more qubits are used. One qubit will influence the other qubit, the data on the other qubit. And here, the data is read in the form of a probabilistic approach. It is not a deterministic. Quantum computing is not deterministic approach. It is a probabilistic approach. That means to have read the data from a quantum machine, you need to run for a single value also, you need to run the algorithm for say 1000 times or 2000 times, and you take the maximum probabilistic value to attribute the quantum output states. It is a probabilistic approach. It is not a deterministic. Right? And I was telling, if you see these modern computers or otherwise our classical supercomputers or your i5, i10 or these latest processors, they are governed by the classical physics laws. They are not governed by quantum physics laws. And they are fully governed by the mathematical logic, Boolean logic. Right? At the base level, we are trying to use only Boolean logic. At a higher level, you are trying to develop some programs over it and some programs over it, and you are able to apply your normal. Now you are trying to apply your machine learning algorithm also. You are making the machines intelligent enough to attain or give us suggestions. Say, for example, you are using these parallel computations. Say, for example, today you have got ChatGPT, which is a very common application platform you are having, which uses large language models, which are again still built on these classical computers. Right? They require very large amount of computations. So, example, if I have to say, the size of a ChatGPT machine, ChatGPT 4 machine, is of the size of almost this college building size, complete college premises, and space cover, the same size is required. Lot of processors, lot of memory, lot of data is stored, and trillions of processing capacity, trillion bytes of processing capacity is required even for a single query that you are trying to make. At an user end, you are trying to just ask some, say, for example, very commonly, recently there was a trending in the market saying that, generate a Ghibli image of mine with something you are trying to give. And if you have to really say, that ChatGPT machine is running at very terabytes of speed and exhaust lot of resource and finally produce your Ghibli image. It is not so easy task. Of course, those innovative people are trying to give us some free resources so that you are going to try to use it and more, and then at the later stage it will be in a paid mode. There also you are using normal classical physics and your normal regular mathematical logics with some enhancements you are using. But whereas quantum computing, you don't have such features. And in your regular electronic circuitry, so for example, if I say there is a block like this, I give some input, you get some output, right? And if the same output is fed back to that block again, you don't get the input same. Same input cannot be ensured. But whereas the beauty of quantum computing is, if you take the quantum circuit, quantum law, if you give the output to the circuit, you can get the input. You can get the input. If you run the circuit in the reverse direction, the original input can be regained. Right? In those we call it as the reversibility of the circuit. When the circuits are reversible, the power consumption at the electronics level, power consumption at the micro level or the nano level or the chip level, whatever I call, they call it as a zero power consumption. They call it as a zero power consumption. Right? As I told, like traditional computers, softwares are designed for the serial communication, and the concept of parallel computation is there with the traditional computers, but you have independently computing parallel processors which are used to compute that parallel task. But whereas quantum computers exhibit quantum parallelism inherently, they are not serial, they are in parallel. So for example, if I say there is a function f of x which is equal to some summation n running from 1 to 100 a plus b, right? ai plus bi. What is that you need to do when the summation x, summation ai plus bi? ai plus bi, at least you need to do the summation at 100 times, right? If you are able to give that A, B, vectors directly to the machine, this parallel computer or the quantum computer will do the computation in a single shot, single clock cycle. The event is single clock. Sir, when this system is such a parallel and such a fast, why we are unable to do? Why these are not so much fascinating? And nowadays, like if something is very good, people are ready to invest in the world. People are ready to invest to the maximum extent and get that done. The very problem, basic problem with our quantum computers is that you require cooling. You are required to access the qubit or manipulate the qubit at a temperature scale of at least 0 degree Kelvin, nearly to 0 degree Kelvin. People are operating quantum computers up to now, the currently available quantum computers are up to 0.17 Kelvin. They are operating at a temperature scale of 0.17 Kelvin. You are all aware that 0 degree Kelvin, if I say, is a state where you are trying to at normal temperatures, you cannot see a electron in normal stage, right? They are either in a spin motion or a circular motion or orbital motion or interaction or vibrating force and all. If you have to say that 0 degree Kelvin means the temperature scale at which even electron or the nanoparticles in the atom are said to be at a stable state, no vibration. Almost that is called idealistically it is a ideal temperature and there is no temperature that can be attained below 273. That was in a theoretical interpretation earlier. And people are now trying to find out a refrigeration aspect up to 0.17 Kelvin they have attained. And our quantum computers are operated at a very low temperature. Even they are operated at a very low temperatures, there are quite amount of noise in the systems, which cannot guarantee the stable state of a qubit. When the state of qubit is not completely guaranteed, you cannot guarantee the results. For that reason, you are trying to run the quantum machine for finite number of times, say 1000 iterations or 2000 iterations you need to take, and that you are trying to get the values on a probabilistic approach. Right? That is the disadvantage with quantum. And people are now trying to find out the errors. Though there are error correction and error stabilization methods, major focus is now on to those error corrections and error methods. If I have to see the introduction of history of quantum computing, this is the history like K.B.N. in 1982. He was the first person who started putting questions to the community to start thinking on. He gave the idea for the people to start thinking on to develop this quantum computing. And he wanted to deal in a computer which deals with probabilistic approach of quantum mechanics. He wanted to simulate life. He put a question to the community and he started his own research into these things which could answer these questions, like can you simulate physics with a normal computer? See, if you want to simulate physics with normal computer, like physics, there are a lot of principles, right? Not at a macro scale, at a nano scale. Those he wanted to simulate, and that is not really possible with normal conventional computers. And he started to make people think new approach. He wanted to simulate time. How do you deal with probabilistic approach, right? He has used the effect of quantum mechanics to build the quantum computer. It is not a quantum computer he has built. He has given a thought process to the community that the next generation computers should be able to develop using these quantum mechanical principles. And in 1994, Peter Shor is a scientist in MIT, 80%. And he is also, Grover is also 80%. Both are from 80. He first in 1994, he gave a theoretical model saying with the quantum computer, you will be able to produce the patterns for a large prime number, right? It is considered to be the toughest problem. Still today, it is considered the toughest problem, and this, due to the toughness only, today's encryption algorithm called as RSA algorithm. RSA means Ravid, Samir, and Edelman. 3 scientists are there, right? Those based upon those algorithm, it is toughest. So that algorithm is used for our encryption. If that is break with these quantum computers, Any password can be broken in the universe. Any password can be broken in the universe. Right? And after the 2 years, Grover, in 1996, he gave another interesting application for your quantum computer, saying that you can do a search, unstructured search, at a complexity of order of root n. That is, say for example, I need to search. Say for example, there is a complete heap. Say for example, heap, Gutlo search here. I want to search. Say for example, I've got lot of notes. A heap of notes. Say lakhs and lakhs. Each note there is one page. I want to search one page. Right? In a normal attribute, if you want to search that page, you need to take each notes, roll all the pages, and you need to at least go through all the notes at least once. Order of n, it should be. But he gave an interpretation. With a quantum computer, you will be able to search at an order of time root n evolutions. It is very, very less. It is very, very fast. Unstructured search. Say for example, if I want to, if people are sitting in a number wise sitting, I want roll number 50. 49 left, 58th I can directly search. But if people are sitting in a random, where is roll number 50? Roll number 50, roll number 50, I need to search every person. But with the quantum computers, the search can be done almost, that too, it is maximum time. Whatever he says is the maximum time. Idealistically, if no errors are there, with a single clock cycle, search can be done. No matter how big the size is. But to avoid that errors and all, to magnify the results, because the result of search is very, very feeble. You cannot identify the search. To identify the search, we try to run for quite number of times to amplify the search result, and then you will be getting the result at the max root n number of times, quadratic times. And if I were to say this shows factorization, it is an exponential speed up. They call it as an exponential speed up. Right? And every quantum computing is attributed as the speed of exponential speed up when compared to the classical computing. Quantum computing is attributed as exponential speed up. Actually, these two algorithms have fascinated people to think and look over, and many universities and research communities started fascinating, and they wanted to invest more and more and develop more and more quantum. Until then, nobody were interested, even though they have the principles. Very specific research communities were onto it. After these two inventions, two people have not given the technology of quantum computers how the quantum computer should be. But with the quantum computers, with the application of quantum mechanical principles, you will be able to produce such kind of results. They gave a theoretical interpretation, and that fascinated people, right? Of course, this slide actually I deleted, but this came. Yeah. 1982, K.B.N proposed first quantum computer, and in 1985, David Goldstahl developed quantum Turing machine. He was the first showing that quantum gate-based model quantum computers can become as a universal quantum computer. Until then, there were different types of quantum computers. See, there are when I am studying, first lectures of my journey into this research, I came across a quantum computer with completely lasers, glass, optics, and all, no cooling and all. I'm searching quantum computers require cooling and all. A lot of refrigeration is required and all. That was thing I was reading. And but I came across one quantum computer which was there in Japan. People developed with optics. Because ultimately the quantum mechanical principles, you require superposition, entanglement, interference, right? And the three important, what was previously I was telling you, superposition and interference. Another interesting factor is entanglement. What do you mean by entanglement? Entanglement. General meaning. Okay, the influence of one is having on the other. So, for example, I say, out of pair of my shoes, I have right socks here. Definitely there should be a left socks also, right? If I have to wear a shoe for my leg, right socks is there, left socks should be there. That is an example quoted in the textbook. But entanglement is the interaction of qubits. They are entangled. When I am trying to entangle, so for example, I take two qubits, idealistically, they say when I take two qubits and when I try to entangle it, right, the state can be, if the two qubits are separated across the distance, no matter, whatever is the distance, right, whatever is the time, any action which I perform on one qubit will be reflected there. That means to say, previously, like after reading this, I used to get lot many ideas at that time. Parakaya placement. Say for example, if there is a mechanism, say for example, if our human brains are there, we have got lot of atoms and memory states in our human brain and all. If I am able to entangle all my memory states with the other person, whatever which is there in here, it is also there. Whatever which I do is reflected there. No matter they are very near or far apart, or it is independent of space and time also. When entangled qubits are separated apart, it is independent of space and time. Right? That means to say when there is entangled qubits, they are used for communication purposes, as I said, security purposes. Right? Today, quantum computers, I said, like, they are able to break passwords, I said. Okay, fine. If they are able to break the passwords, can these be used for security purposes? Definitely. These can be the finest security algorithms you can develop with the quantum computers with the principle of entanglement. See, for example, the two parties, Alice and Bob, we call it as Alice and Bob, A and B, right? They try to take a pair of qubits which are entangled, and one qubit is with Alice and another qubit is with Bob. In between, they transmit their data. With the entangled qubit, that person will try to decode. The receiving person will try to decode in an outer sketch, right? If any person in between the channel tries to get the access of the data, finish, collapse. The other person will understand that, oh, this is not my data. Definitely. That is how the entanglement principle is used for that purpose. Of course, in 1997, this low grower has given research algorithm. In 2016, IBM researchers announced the availability of quantum computers. Until 2016, quantum computers were there. Now and then previously also quantum computers were there. It is only the first person, IBM, who have developed these quantum computers, have made available to the public. He is not the first person to develop quantum computers. There are many players in the market who developed quantum computers, but he was the first person to give it to public. And in 2019, Google came out with an algorithm working on its quantum computers and stated that quantum supremacy stating that the strange properties of quantum mechanics carried out with quantum computers produce exponentially faster results. Theoretically, they are proven with their machines, exponentially faster results can be attained over the classical machines. But what algorithms or what problems can be dealt on the quantum machines? Idealistically, any problem can be dealt on a quantum machine, but only the problems which are very hard, classically hard problems are advised to use quantum machines, because anyhow in a classical machine it is very hard, it is very difficult, expensive. So make a try on a quantum machine. If it is executable on a classical machine, don't go for a quantum machine for that problem, because executing algorithm on a quantum machine is very costly at present. Maybe in future it may reduce, that is a different story. At present, definitely executing an algorithm on a quantum machine is a costlier. Why it is costlier? Definitely it is very costly. See, it is not just the quantum machine which is there. Quantum machine is provided by Google IBM or Google or any other player in a cloud. To provide the job to the quantum computer, there are many of supercomputers which are required, like a large data storage and large processing machines are required to put it in a pipeline, send it to the machine, run for finite number of times, correct the results, interpret and give it to the user. Lot of resources are required. And idealistically, when I came to understand the power requirements, almost power requirement for running a quantum computer is nearly like the power requirement for a small village. Small village, quantum computer, the refrigeration power computing normal power ఎంత కావాలంటే విలేజ్ కి ఎంత కావాలో అంత పవర్ కావాలి. అదే చాట్ జీపీటీకి అయితే ఆల్మోస్ట్ మన విజయవాడ సిటీకి ఎంత పవర్ కావాలో అంత పవర్ ఒక చాట్ జీపీటీ మిషన్ కావాలి. I actually came to know that real statistics from one of my friends who is there in Intel, who works for the processors which are Intel and NVIDIA, who gave the infrastructure facility, and it is almost nearly a power required for Vijayawada anta kavalo anta chat GPT machine ki తీసుకుంది. అంటే టోటల్ పవర్ అలానే కంటిన్యూగా అంటే క్వాంటం కంప్యూటర్ రన్ చేయాలంటే మనకు ఒక స్మాల్ టౌన్, ఫర్ ఎగ్జాంపుల్ మనం వన్ టౌన్ మొత్తం అంత కలిపితే ఎంత పవర్ కావాలో అంత పవర్ క్వాంటం మెషిన్ ఒక్కటే తీసుకుంటుంది. దాని చుట్టూ ఎలక్ట్రానిక్స్ మేబీ లైక్ అనదర్ గిగావాట్స్ ఆర్ సంథింగ్. As I have told, like quantum bits are called as qubits. The major principles which are governing are superposition, entanglement, interference. Right? What is meant by superposition? It is an ability of a state to exist in more than one state at a simultaneous time. Same time. It can be either state 1 or state 0 or both combination of state 1 and 0. Idealistically, I have not given the equation. I don't want to put you in an equation state. Like, if I say the state psi, the quantum state psi, if I call it as a psi, which is equal to alpha times 0 plus beta times 1. Right? Alpha times 0 and beta times 1. That means if alpha is 1, beta is 0, the value is 0. If beta is 1, alpha is 0, beta is 1. Right? That is how the states and the alpha beta values can be between 0 and 1. Say 25% 0, 75% 1. That percentage varies. The representation of a qubit, the convenient way to represent a qubit is given by a block sphere. For example, if you Google it, everywhere you will be getting block sphere. I don't want to confuse that because that's the reason why I have not picked out my PPT. This is a general PPT which I have taken from ChatGPT. It is not instantaneously, it is PPT which is created by ChatGPT and it is not my own. I got my own PPT which is completely into research domain. Yeah, talks of some other terminology which confuses you. I don't want to put mathematics in front of you and get it confused. And the primary requirement to understand this quantum computing is linear algebra, matrix algebra. Matrices, everywhere you find large matrices. Matrix inversions, matrix complex conjugates, everything matrix. Matrix ఎట్లా ఉండాలంటే ఆల్మోస్ట్ అసలు పెద్ద మ్యాట్రిక్స్ తీసుకునే మనసు 2 డైమెన్షనల్ గా తీసుకునే మ్యాట్రిక్స్ కూడా కాకుండా 3 డైమెన్షనల్ 4 డైమెన్షనల్ n డైమెన్షనల్ మ్యాట్రిక్స్ తీసుకుని మనం కంప్యూటేషన్ చేయాలి. సే ఇఫ్ ఐ సే లైక్ 5 క్యూబిట్స్ అంటే 5 డైమెన్షనల్ మ్యాట్రిక్స్ తీసుకోవాలి. మనం మామూలుగా 3 డైమెన్షనల్ వరకే మనం మామూలుగా గుర్తించలేదు. కంప్యూటేషన్లో వచ్చేసరికి ఎన్ని క్యూబిట్స్ తీసుకుంటే అన్ని మ్యాథమెటిక్స్ అంతవరకు, రైట్? కొన్ని స్టేట్స్ 0 అయిపోతాయి, కొన్ని స్టేట్స్ 0 అవ్వకుండా ఉంటే అవి ఉన్నవి మాత్రమే మనం అట్రిబ్యూట్ చేసుకోవాలి. అండ్ ఎవ్రీవేర్ ది ఎలిమెంట్ ఆఫ్ ఎ మ్యాట్రిక్స్ ఇస్ ఎ కాంప్లెక్స్ ఎలిమెంట్. రియల్ నెంబర్, ఇమాజినరీ నెంబర్ రెండు ఉన్నాయి. And as I told, this entanglement, qubits become linked with any other effect, they are instantaneously covered. So for example, so for example, if I am able to do some process, if I am able to get all your quantum states, or if there is a process of entanglement of all my quantum states with other person, I can say that my mind is completely simulated, right? Quantum mechanically it is proven. I understand that Parkai Pravesman is working on it. Quantum mechanics. I made myself, yeah, it could be true. And how do you align or disentangle all the quantum states with the other? When your energy states all together matches, there is an entanglement at one state. Interference. And out of all the states, when I'm trying to tell you, like, parallel computation is possible in 0 to n. 0 to n అంటే 0, 1, 2, 3 ఓన్లీ ఇంటీజర్ నెంబర్స్ కాదు, ఫ్రాక్షనల్ నెంబర్స్ కూడా అయ్యొచ్చు కదా. when I say not only integer numbers, fractional numbers కూడా అయ్యొచ్చు. But when I'm trying to this interpretation, there are several interpretations of understanding the quantum computing. Say if I am trying to take a wave, quantum wave, quantum computing is a wave. One, see, how do you find the energy state of an electron? See, electron is a charged particle revolving around the orbit. If it is in a constant speed, at a constant space, you don't find anything different. But definitely it is not only revolving in this direction, it revolves with sometimes like this big and sometimes small ground state. Always it tries to come to ground state, but it will not be stable in the ground state. So for example, there is a person who is running in his own track, right? There is a friend of him or her running besides him, will push. Either he may go inside or he may go out. When he goes out, or otherwise he goes to higher excited state, and again, no, I am out of the track, I want to come back. What will he do? He will come back to the normal state by giving out the excess amount of energy he gained to move out. Right? Similar way. And that excess energy is captured out, and we say that is the state of that electron or atom or whatever is the information attribute we are going to find out. All these, when there is a move like that from higher energy state to lower energy state, the energy is given in the form of a wave. The waves given by two or more entangled qubits produce the similar energy pattern. Some energies produce higher amplitude, some energies produce lower or nullified amplitudes, which produces interference. Only those patterns which produces the constructive interference pattern exist, and we will be able to record. Destructive interference pattern we are unable to record. Right? When you try to, this is beauty of this quantum computing is the output of the state. When you try to measure, after measuring, state is dead. We call it as a quantum state collapse. Quantum state collapse. My interpretation, actually, this is not there in any of the textbooks and all. My interpretation, say for example, if I take a tripling ball, I have a ball. I say I am trying to triple it between ground and this place. Continuous, very continuous, where you are unable to distinguish whether it is in the ground or in here or in between. Where the ball is, you don't know. Through some process, what I try to do is I put some magnet or catch kind. At that instance of time, if I am able to catch here, I say it is in the up. If I am unable to catch, it is in the ground. But at that point of catch, it may be in between also. If I am able to catch here, I put a catch here and a catch in the ground, both. If I am able to catch at the top, I'll say it is a 1. If I am able to catch at the bottom, I'll say it is a 0. If I am in the in between, because I want to ultimate, even though it is capable of holding the values between 0 and 1, and in between 0 and 1 also, in between 0 and 1 I am not able to, or I cannot measure. I will be able to measure whether it is 1 or 0. Once if I am measuring, a tripling ball man hold chesi sangal. Because a hold chain, that is different. Once if you are holding, you are trying to determine whether it is 0 or 1. That is what is the measurement. Once if you have measured, the state is collapsed. The natural state of the vibration is collapsed. Once it is collapsed, of course, after releasing it, it again goes to its state, but it is not the quantum state which we are trying to attribute. We measure, once measured, we say that quantum state is said to be collapsed. Right? This is one way of measurement. There are various ways of measurement. See, if I am trying to, I have given the example saying it is a tripling like this, but in a reality, that movement of that electron could be in all 365 degrees. Either circular, vertically like this, horizontally, or in axis, x, y, z. All the polar coordinates are possible for our interpretation. This is all in a 3-dimensional only. If we are considering, it is not only 3-dimensional, it is n-dimensional, not 4. It can be n-dimensional. But the measurement process can be between only these 3 dimensions. Measurement process or understanding process. I say that I put a catch bottom or up or left or right, we say that we are trying to put only in these 3 dimensions. And between these 3 dimensions only we are trying to get the state of the cube. Right? Whenever I am trying to measure, I am not putting this side, when I am trying to measure, state is said to be collapsed. The state in the 3-dimensional polar coordinates are captured, and that is given out for each cube. Right? There are various interpretations. So, for example, if I am trying to, before the quantum experiment running, I put my qubit to state 0, say with this axis. My measurement also should be in this axis. Whatever the state axis or we call it the basis we use for initialization of qubit, the same basis should be used for measurement. If the basis is different, you will be getting answer different. It cannot be interpreted, right? That's what. When I was trying to tell you the teleportation or otherwise, your data encryption which is there for transporting of information, two entangled qubits are there. They are getting separated, and this Alice and Bob share those bases of measurement. Whatever is the basis which Alice tries to use, the same basis Bob should use. Same basis. Right? Since they are entangled, when I say that they are entangled, if this Alice changes the basis, Bob basis is also changed. Bob basis is also changed. And only these two persons can get the information. If there is an in-between person, they don't know the basis. What basis? Out of this 365 degrees lo ఏ యాంగిల్ లో ఎన్కోడింగ్ జరిగిందో తెలియదు. తెలియడం కోసం వాళ్ళు they try to capture. See, it is again a photonic wave which is transporting. If they capture it, it is collapsed. Basis తెలియడం కోసం మనం అదే బేసిస్ లో ఒక బేసిస్ లో పెట్టి మెజర్ చేయాలి. See, if it is all again a confusing topic, but on an outsketch I am telling you, it is the most secure process that can be attained through quantum computing, and people have developed completely secured channel which can be transmitted over air or fiber optic cable and all. It is one of the successful technologies which is implemented with quantum encryption standards. For communication, it is okay, fine. It is good, right? They solve certain exponentially faster problems. The applications of quantum computers, the major expansion is into this. They are exponentially faster to solve the problems. They break RSA algorithms. They can simulate the molecules for drug discoveries. Say for example, if I am trying to simulate, say for example, there are two interactions. One is H2O molecule is there. H2O, hydrogen and oxygen. I want to simulate it. In a normal classical computer, simulation is very tough task. Simulation is very tough task. So, for example, I try to build a model which is simulating H2O. Suppose there is another person coming, I want to add one more H. How the structure will be, how the interactions will be. The interactions, everything has to be simulated, and that simulation is very tough task. So, for example, I want to design a drug. At the COVID time also, people were trying to design a drug. If a drug is designed with some chemical structure, that structure has to be simulated first, and that structure is developed in the lab and tested on various other organisms or other interactions, how they will be. Those interactions, simulations are very difficult tasks. Still today they are termed to be very hard task for the supercomputers which are available in the world. Those kind of simulations can be done with these quantum computers because they are fundamentally using those quantum mechanical principles itself in simulating those structures. It is very easy. And they are used in optimization problems. So, for example, very common optimization problem. Why these optimization problems are very important in computers are because, for example, I want to travel. Traveling salesman problem is a very common problem which every computer science people say that this is very difficult in running an algorithm. They try to find out some heuristics algorithms. Deterministically, they are not having any concrete rule saying this is the lowest possible this thing, right? But with quantum computers, we can try to find this optimization problem, because see, the information is attributed to atoms or molecules and all, right? Whenever the information is there, they try to take based upon the values, but ultimately they come down to the ground state. See, it is a natural tendency of the atoms or molecules or those particles which are having energies, they try to come down to some ground state. We call it as a ground state. When it is able to come down to the ground state, and when the information is found out at that ground state, that is the minimum possible energy state. We call that as a minimum possible energy state, and that we can say as an optimization problem. Those are done through some annealing kind of quantum computers. The optimization problems are done through annealing. We call it cooling, lowest energy state. Different technologies are there. As I said, like superconducting quantum computers are there. Majorana kind of quantum computers are there. Annealing kind of quantum computers are there. Recently, Microsoft came out with the new architecture. Right. These architectures and all, the dynamics is different, completely backend. We call it as a device physics. Another technology is a trapped ion based quantum computers are there. And most of these quantum computers, to our understanding, this IBM or Google, many other gave out with the model called as the gate-based models, quantum gates. Just to be, in our classical computers, we have got gates, AND or NOT gates, right? Which take two inputs and give one output, like AND gate, OR gate, and not AND or NOT. These three are fundamental gates. Any circuit which we say can be built with these three, right? Of course, NAND and NOR are called as universal gates, where these three fundamental gates can be derived from those main gates. So anything. Here you have got different gates like Hadamard gate, NOT gate. I'm not going to give you all these gates. There are also some gates, quantum gates, which I say a gate to put into superposition state, a gate to rotate in X direction, a gate to rotate in Y direction, a gate to rotate in Z direction, a gate to spin it, right? A gate to control this spin based upon the other value, right? Like that way, there are different quantum gates which are there, and they require very low temperatures, almost at 0 degree Kelvin, almost near to the 0 degree, sub Kelvin temperatures. They are sensitive to noise. And one more fundamental thing which I need to get clarified is, see, when there is an electron revolving around or spinning around, right? They go from lower energy state to higher energy state. From higher energy state to lower energy state, they come down. This is called as relaxation time. I will call it the relaxation time. Your computation should be taken out within this relaxation time. Otherwise, you don't get the values. Computation should be very, very fast. If relaxation time is very small, see, ఎట్లా అంటే ఫర్ ఎగ్జాంపుల్ ఈ రూమ్ నుంచి దొంగతనం చేయాలంటే ఒక పర్సన్ ఏం చేస్తాడంటే తలుపు తెరుస్తాడు. తలుపు తెరిచి తలుపు మూసే లోపు ఇక్కడి నుంచి తీసుకెళ్ళవలసినవన్నీ తీసుకెళ్ళిపోవాలి. మళ్ళీ మధ్యలో వేసేస్తే కుదరదు. సేమ్ వే ఆ రిలాక్సేషన్ టైం లోపల బిట్వీన్ దట్ రిలాక్సేషన్ టైం ఓన్లీ యూ నీడ్ టు get the quantum information or quantum information processing interactions. Everything has to be done only in that stipulated coherence time. We call it as a coherence time, right? Relaxation time. If you are unable to get that, they are sensitive to noise, right? And the limitations, high error rate. Results guaranteed. Results are not still guaranteed. They are having very high error rate. Of course, people are trying to build parallel circuits over it, do the finite number of computations. They increase. Initially, they used to do probabilistically 500 times circuit running. Now they are trying to run 1,000 times, 2,000 times, more and more. And qubit coherence, short lifespan of qubit states. People initially developed with 1 qubit, 2 qubit, 5 qubit. Most of the time, when I was started my research, 5 qubit machine was the most commonly available machine. Because 5 qubits, see every qubit, when I say 5 qubits means every qubit has to interact with every other qubit. They should be very, very near. One-to-one interaction will be there. If I am trying to increase the number of qubits, every qubit has to interact with every other qubit. Right? Every qubit has to interact with every other qubit. When qubits are increased, the interaction matrix, and when I call it the interaction matrix, are the energy computations between these qubits will increase more and more. The complexity of system increases more and more. And the complexity of system increases more and more. All the qubits have to be handled at the same coherence time, short lifespan. All the qubits are to be processed at the same coherence time and between that interaction time. Right? Scalability, it is very difficult to build large quantum systems. The reason why it is very, very difficult is I can increase see, in a conventional computer, if one processor is not sufficient, what you do is you take a motherboard, you put another rack, another processor, you can keep the same bus you share the memory and all, it's sufficient. But here it is not so. If you try to increase the qubit, that interaction between the qubits should be increased. When the interaction increases, the coherence time would not be sufficient enough to get the processing of the data. Right? Quantum computers of today are not in a better way to do everything. That is the reason why only few computations are suggested and not all. Right? Major players, now there are 100 plus players. Not 100, now there are more. Now major players I can say is IBM, Google, Microsoft have recently started its journey into it. Intel, ST Microelectronics, Honeywell, IonQ, and many other players are there. They develop their own quantum computers. Apart from these quantum computers, these are called the gate-based quantum computers. There is another very famous quantum computer system which is called the D-wave quantum computer system. As I told previously, I was telling you there is a property called as minimization of energy, like annealing kind of quantum computers. D-wave quantum computers are based upon annealing based quantum computers. They are developed only for a specific task. See, these computers like IBM or Google or Microsoft, they are gate-based quantum computers which can be used for general purpose. For many applications they can be used. But D-wave quantum computers are there. Say if I have a particular task, problem is there, your computer is designed to work only for that problem. It cannot be generalized. D-wave will produce they have produced such kind of quantum computers which are specific to a problem. They were successful enough for certain applications like share trade predictions, US share trade predictions, they are able to apply. Similarly, share market, see the speed of a quantum computer is a computer, otherwise supercomputers are very much utilized by these kind of platforms like, share trading companies are the persons who are trying to invest more and more. When they say that, this is a very fastest than every other thing, yes, they try to implement it, and one such for that financial purposes, it is being developed, and in that way they are successful enough, right? That is DWF. It is in the finance and logistic optimizations. For many of these optimization problems, they try to use this. They use by D-wave computers and machine learning. As I said, all these quantum computers are completely based upon these matrix interpretations, and they are all completely probabilistic approach. If you try to see the machine learning is also matrix based. All probabilistic approach, and there is no deterministic approach in a machine learning, right? So people have tried to see, when you try to see the mathematics behind, almost they try to have similarity of the mathematics, and that is the reason why people try to use this machine learning, modern day machine learning algorithms on a quantum computers. See, machine learning algorithms on a classical computers, which are very, very difficult to simulate or to run, they can use this quantum computers, and that is the reason why quantum machine learning is one of the subdomain of quantum computation and AI, which made people to run about on this machine learning, right? And for all these platforms, because these are recently built, they use Python as a base language. Python is a base language. IBM provides one such development of programming environment called as a KISSCAPE, Quantum Information Science Knowledge Interpretation Tool. SURC is by IBM. SURC is by Google. This is also Python-based programming approach. Q# is again Python-based programming approach, which is designed by Microsoft. And there are different simulators which are used for testing this quantum computation. Before you run your actual quantum computing program on a quantum machine, every of these platforms, like IBM or Google or Microsoft, they gave simulators. You can run your quantum program on the simulators, see whether it is running fine, then only you are ready to run on the quantum computer. Right? Every of these players give us some APIs, application program interface, how to handle it, that's it. They don't give us an access directly to the quantum computer to access it. They will give you will be having a free cloud access. Every of these quantum machines are given through cloud access because those resources are so expensive, and they want people more and more to use, right? For example, this KISSCAPE IBM people, they give 10 minutes access for our purpose per month. They also may be giving half an hour per month. So these people like Microsoft are not tried it, but they are also giving they may be giving some 10 minutes. This 10 minutes means it is very, 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 very high for us. So only 10 minutes. See, the time of our job execution is only 10 minutes maximum. See, when I try to send my job over the quantum computers, the queue will be, our job will be in queue for 1 day, 2 days, or sometimes if I am lucky enough, I may get in within 1 hour. Sometimes I have faced my problem, like my job is there for 2 days, 3 days and all, right? After that, I may get a chance and my job is executed in some 100 nanoseconds or 200 nanoseconds, and 10 minutes I have never utilized completely in 1 month with one ID. Suppose if you are exhausted with one ID, with other Google ID you can get another mail ID, for mail ID you will be getting 10 minutes. That is not a big issue. But that 10 minutes is not completely utilized. Your job will be kept in a queue for longer time, and in month utilizing that 10 minutes is it is not a limitation. Right? Initial days, like when I started my journey with 5 qubit machines, my job used to be getting access within minutes. There is no queue time at that time. Now there is a queue time. Now people started to use more and more, and this IBM people, And many of those IBM systems have got retired. Because qubits, as I said, like those interactions are there. There are quite errors, right? When I'm trying to access or compute or give certain classical value to the qubit, that means I'm trying to give some energy to it based upon my classical value. So, for example, in 100, let's 153 and a value in qubit machine ki value. 1 another energy, 5 another energy, 7 another something like the equivalent energy in a they are getting energy. The interaction between the qubits also gets at certain energies at some computation, their interactions. Three qubits much I try to put some interactions, right? Over certain computations, those qubits will not be able to come to the ground state again after this computation. If they are not coming to the ground state, they require correction. Majority of the time, these quantum machines, suppose if there is a day, in a day, mostly half of the day they will be using for corrections only. Say for example, some 10 jobs they take up. After 10th job, they said that okay, more errors are coming, right? So they do some corrections. They'll stop taking the job and they'll try to do some corrections. Say if the same quantum machine, if I am trying to run my job, I got one result right now. After some time, if I run the same job, I am not guaranteed that I will get the same kind of results. I need to take the maximum probable value. And that is the reason why you require to run for finite number of times called as shots. In the conventional machine learning algorithms, we call it the epochs. Here we call it the shots. The epoch is complete run. Here, the quantum job you are trying to, wherever the quantum is required, you use that quantum and come back. That's it. Right? And of course, it has got its own way. To my guess, it may take another 5 years, not 10 years. Another 5 years, it should be usable because every player, as I told, like IBM or Google or everybody are trying to invest more and more and trying to work hard throughout the world, and they are trying to provide these quantum machines for free access for more number of users to come out with more algorithms, with the innovative application thoughts of how they can use these quantum computers. If they are using it, they are trying to produce more and more quantum computers, and widespread usage will be there. Otherwise, if I have to say, at present, if I say e moment lo any quantum computers run avutunnayi, I can say less than 100. There may be thousands of quantum computers. Every quantum computer after finite usages they will be retired. Retired ante avi inga panchi. Enta correction chesina correction kavu. A chip ayipothe. A chip ayipothe inga complete ఆ సర్క్యూట్ ఆ రిఫ్రిజిరేటర్ కూడా ఆ చిప్ మాత్రమే పనిచేస్తుంది. అది పనిచేయనప్పుడు ఇంకా అది అయిపోయింది, దాని సర్క్యూట్ అయిపోయింది, ఫినిష్. అది రిటైర్ పక్కన పెట్టి. సి ఆల్మోస్ట్ క్వాంటమ్ కంప్యూటర్ ఎంత ఉంటుంది? పెద్దదా? ఇందాక చూపించిన డయాగ్రామ్ ఉంది, రిఫ్రిజిరేటర్ పెద్ద డబ్బా అంతా చూపిస్తారు చూసారు, అంతా రిఫ్రిజిరేటర్. క్వాంటమ్ కంప్యూటర్ అంతా కలిపినా మన క్రెడిట్ కార్డ్ సైజ్, డెబిట్ కార్డు, క్రెడిట్ కార్డులో హాఫ్ సైజ్ ఎంత అయితే అంతే చిప్ సైజ్. అంతే మన రెగ్యులర్ ప్రాసెసర్స్ ఎంత ఉంటాయి అంతే సైజ్. సే ఇవాళ ఉన్న 1000 క్యూబిట్ సిస్టమ్ కూడా అంతే సైజ్. దాని చుట్టూతోనే ఎవ్రీ క్యూబిట్ యాక్సిస్ కి యు ఆర్ ట్రైంగ్ టు కూల్ ద సిస్టమ్. అంత అవుటర్ సర్క్యూటరీ కూలింగ్, రిఫ్రిజిరేటరే ఇంపార్టెంట్. క్వాంటమ్ కంప్యూటర్లో మేజర్ రిఫ్రిజిరేటర్ and supporting elements. And whoever quantum computers, so they can start your journey. Who should start your journey into quantum computers? people in physics, people in chemistry, people in mathematics, people in computer science. Even people in the marketing division like MBA also. They can also use they use quantum computers and explore more. Right? There are many players who will provide quantum computers for usage, right? And lot of help is available. Lot of help is available from IBM. Lot of help is available from the IBM. There are third-party players like Penny Lane is one such platform which gives you access to these different quantum computers, not single IBM computer. They'll give access to different quantum computers. Front end, you can use your Jupyter notebook and Python language, and you can connect to any quantum computer or cloud, and your job can be done. Right? And as of now, the suggestion is the jobs which are very difficult for a classical computers to execute are only suggested to be used on a quantum computer as of now. But for learning purposes, people are trying to run normal, classically computable problems are also on a quantum computers only for learning purposes. Right? Whatever are the examples which are provided by those service providers in a learning platform, like if you take IBM Quantum, if you just Google it and say IBM Quantum, there you say learning, they'll give you step by step, day by day process to learn how to proceed with the quantum computers. Right? అంతేగాని ఇంకెక్కడ కూడా ఎక్కువ మంది ఎవరు టీచ్ చేసినా కానీ అక్కడి నుంచి టీచ్ చేసి. For example, if you see just do this. You Google it, you can get. Just say IBM Quantum, you will be getting lot of documentation which is available on the IBM machines. You say tutorials, there are a lot of tutorials. Even though you say that you are at zero knowledge, if you want to start your journey into quantum computing, I suggest you go with this IBM Quantum. You have tutorials, resources of how to study and all, books, research papers, everything. From something like, from KG to PG, whatever is the level of learning into quantum computing, for every level of learning, this platform is going to give you a good help. There is nothing which is difficult. There are quite a number of video lectures which are available from IBM, which teaches you just like cakewalk. They teach you very easy. There is nothing difficult for you. Small video lecture, any video lecture which is not more than 10 minutes or 15 minutes. Longest video, if there is a continuity of the topic, 15 minutes. Otherwise, every video lecture, they will cut short each topic into small parts, 10-15 minutes. Easy to grasp, right? You go with these tutorials or you go with this documentation and all. Documentation also, all over you can get. You can see different quantum computers, how to explore and all. I suggest you go with this platform. There are other platforms like Penny Lane. This is another platform which is a hybrid, not specific to IBM. This sheet is specific to IBM. This is a platform, which, ecosystem which provides interface to various other quantum computers, as I told, like quantum computers from IBM Q, IBM Ion Q, D-Wave, Microsoft, Google, all the quantum computing layer services are provided through this platform, which they give some free access, right? They give suggestions for your problem, which quantum computer is sufficiently good. Because every quantum computer cannot be applied for every problem that we try to design, right? There are certain quantum computers which are specific to some applications. These kind of platforms are there. Not only this, there are various platforms which even our Indian government CDAC Pune has developed some quantum computer interfaces which they give access. Say for example, if you are going through IBM Quantum directly, they will be giving you 10 minutes of access. Through CDAC Pune, through their website, and you get a login from their credentials and all, they will give you access to some more quantum machines which are not visible to the normal users. For regular users, say for example, for learning, only few systems are visible. So for example, if I try to see this IBM Quantum, if I say only few systems are available. If you go with the sign-in platform, you can sign in. Oh, sorry. I should go with this. You can sign in with your Google ID. This is my VAT student because I am research scholar there. I am continuing there. See, there are a lot of web resources which are available in the videos about this quantum computing and all. QPUs, So these are the various quantum machines which are there. IBM, Kingston, Greece, they name it. They may be at different locations in US. Similarly, after a few days, you will be having only retained QPs. These are all retired QPs. Retired and they such pen. Emission and such pen quantum computer. They cannot be used. Currently available like these are currently available quantum computers which are there. Right? 6, 1, 2, 3, 4, 5. These 6 are available. And then the 5 qubit missions, 127 qubit missions, and they retired due to errors. They are using this processor type called Heron. Of course, IBM documentation with the processors different types. Qubit interactions different types. Right? This is from my side, like if you are not asking any questions, I will not be able to tell anything. Now it is a question open. I'm opening for a question unless you ask. I cannot come out with anything says. See, this is an upcoming technology which will definitely be prevailing for the next generations. Definitely. Because now people are much focused on it. People are trying to invest, and there are a lot of breakthroughs in the industry.
What is the basic objective of this quantum computing? Is it for the speed or secure transmission?
It is not just for speed. It is the next alternative for normal computation. Because see, in a normal silicon fabrication type, we have come down to a scale of nano dimensions. When you cannot make smaller and smaller and still smaller. You have already come to a stage where these atoms are very close to each other. When you try to interact with these atoms that are very close to each other, quantum mechanical principles are prevailing than the classical mechanics. When quantum mechanics are prevailing over the classical mechanics, you need to definitely go for a quantum applications.
There is an alternative to
normal computation. That is the next generation computation. For a speed is one aspect. The other is, see, you already come down to a very small, and if you are trying to develop circuit with such a nanosecures, you cannot increase more speed.
Actually, Hadoop ecosystem is there. So they are also coming from different nodes, and they are also good performance with respect to the queries. So what may be the difference?
Hadoop, which cloud platform. Yeah. Even though they are trying to develop, see, a number of processes are there, independent. See, when there is a computation, say for example, if I say sigma A plus B, I running from 1 to n, I take n such process to do this A plus B, independently they are machines, they are interlinked, and you are getting parallelism through individual processes. But here, the parallelism is done by principle itself and is inherent by the quantum principle. You don't require n number of processors. It is a single processor which is doing that parallel process. Pardon?
How was that happened? Single.
I said like superposition is there. The principle of superposition, interference, and those computations which are to be living are to produce with constructive interference, and those states, quantum states, are so proposed of one over the other. That means to say 0, 1, 2 qubits are there. 0, 1, 1, 0, 0, 0, and 1, 1. These are the 4 quantum normal states which we can realize with normal qubits, normal bits. In a qubits, combination of these ranges very high. Even though with the 2 qubits, you can produce more number of combinations. And out of those more number of combinations, ultimately you are going to realize only these 4 states. But in between computations, see, in our normal computation, you are realizing only the computations which are specific and deterministic. In between computations, you are not able to do. But this parallel, okay, all these computations are done at a parallel, and final result can be taken only from these 2 qubits. That is how they are parallel. Superposition, interference are those 2 principles which are governing for this parallelism. And one more another thing is, there is another thing called as no cloning theorem in quantum computing. You don't have a memories RAM. You don't have a RAM. RAM possibility is not there with the quantum computing. You cannot copy. There is no copy. No cloning. You cannot copy.
Qubits
Cannot be copied.
One qubit like communication. In communication, as you said, 2 qubits can act like same.
Yes, that is through entanglement.
Yeah, entanglement.
Entanglement, it is not copy. It is not a copy. Entanglement, I said, like, simple aspect is something like if I say a stable atom is there, stable orbital state is there. One electron should be in up state, one electron should be in a down state. Spin states, 2 opposite spins, we say it is a stable. If I am able to capture one spin state as up state spin, if it is a stable state orbital, there should be opposite spin, definitely it is opposite spin. I am trying to separate it and put it in some other place. But they are not copy of it.
But they will act same.
Contemporary. That means they are entangled. Suppose if I am trying to alter the direction of the spin here, inherently there is an alteration there. No matter they are separated in a large space. Right?
Into different realms also, they will act like
Same. So, example, like, when I was trying to get the insights of quantum computing in the initial days, one of the famous lecture which was given by one of the scientists gave an example. In my childhood days, there used to be one serial called as Star Trek. చిన్నప్పుడు దూరదర్శన్లో నా చిన్నప్పుడు దూరదర్శన్ వచ్చిన కొత్తలో స్టార్ ట్రెక్ అని ఒక సీరియల్ ఉంది. సెల్ ఫోన్ ఇట్లా ఓపెన్ చేసి ఫ్లిప్ ఫోన్, అప్పుడు ఫ్యాంటసీ అండి, మేము స్కూల్లో ఉన్నాం. మనిషి చూసి అవతలకి మాయమైపోవడం, ఇక్కడి నుంచి అక్కడికి మాయమైపోయాడు. అది ఎట్లా పాసిబుల్? అప్పట్లో ఫ్యాంటసీ. క్వాంటమ్ మెకానికలీ ఇట్ ఇస్ పాసిబుల్. If through some process, if I am able to entangle all my quantum states with the other person, I am able to move to any other place in the world or universe. In the world or universe or another space or anywhere. If quantum states are simulatable, I can move to any other place. Similarly, quantum information can be done in a remote. Say, for example, the same kind of technology, it is a quantum technology only. You have got FRAMs today. FRAMs are there. Today in our quantum computers, to storage our data, there is some electronic circuitry which goes physically to that location, write the data and come. Right? Now through some these FRAMs and all, there is no process. నేను ఇక్కడ రాస్తే అక్కడ మిషన్ మీద రాయొచ్చు డేటా. Say for example, I can write the data somewhere. For example, నేను ఇక్కడ కూర్చుని ఇక్కడ మౌస్ కదిపితే అక్కడ కదులుతుంది పాయింట్. Similarly like that, they may be separated across and they have some other communication channel, but it is remote. Remotely wireless connection through FRAM technology, which uses the quantum principles, where I can write here in my local machine and the same data can be written there in some other machine. No, that is there. those are called as FRAMs. అట్లాగే quantum technologies కూడా అట్లా.
Sir, what are the opportunities that there for this area? Opportunities, companies ఎట్లా ఆఫర్స్ అనేవి ఇష్యూ చేస్తారు ఆపర్చునిటీస్ అని.
ఆపర్చునిటీస్ అన్నవి ప్రస్తుతానికైతే లిమిటెడ్గానే. జాబ్స్ ఎట్లా వస్తాయి అన్నది రియల్గా కంపెనీస్ ఏపీ కాంట్రాక్ట్ మీద పనిచేస్తున్నాయి, ఎంత జాబ్స్ వస్తాయన్నది నిజంగా ఆగదు. నేను రీసెర్చ్ కమ్యూనిటీలో రీసెర్చ్ మాత్రమే చేస్తున్నాను. మోస్ట్ ఆఫ్ ది పర్సన్స్ ఆర్ స్టిల్ ఇన్ ద రీసెర్చ్, బట్ పే అయితే చాలా ఎక్కువ. వెరీ లిమిటెడ్ కంపెనీస్ పే అయితే. వాట్ ఐ కేమ్ టు నో ఫ్రమ్ మై గైడ్ ఈస్, రీసెర్చ్ స్కాలర్గా కనుక బయటకు వస్తే 10 lakhs per month మినిమం శాలరీ వచ్చేదానికి అవకాశం ఉంది. అంటే ఆయన క్వైరీస్ వచ్చి అట్లా వచ్చింది.
Okay, but what sort of things we need to suggest if a person wants to get into that? అంటే నువ్వు ఇది నేర్చుకో, లేకపోతే if I want to get into that, what are the things I need to learn? మ్యాథమెటిక్స్ లీనియర్ ఆల్జీబ్రా ఫస్ట్ అండ్ ఫార్మోస్ట్ లీనియర్ ఆల్జీబ్రా. అది మాత్రం అసలు మ్యాట్రిక్స్ ఆల్జీబ్రా. లీనియర్ ఆల్జీబ్రాలో కూడా మ్యాట్రిక్స్, ఎడిషన్, మల్టిప్లికేషన్, ఇన్వర్స్, కాంప్లెక్స్ కాంజుగేట్, హెర్మిషన్ మ్యాట్రిక్స్, కన్వల్యూషన్. నాట్ అట్ ఏ నార్మల్ స్కేల్, కొంచెం హెవీ స్కేల్లో విజువలైజ్ చేసుకునేంత కెపబిలిటీ రావాలి. దట్ ఈస్ వన్. అది అసలు బేసిక్ ఫండమెంటల్ ఏబిసిడి ఓరమ్మ లాగా. దెన్ ఆఫ్టర్ దట్ యూ కెన్ ఫాలో దిస్ కైండ్ ఆఫ్ IBM కైండ్ ఆఫ్ ప్లాట్ఫామ్స్. అవన్నీ వాడు దాంట్లో మ్యాక్సిమం ఇదివరకు ఉన్నంత కాంప్లెక్సిటీ లేదు. నేను రీసెర్చ్ స్టార్ట్ చేసిన ఈ 5 ఏళ్లలో నేను స్టార్ట్ చేసి నేర్చుకున్నప్పుడు నా పాత నోట్స్ అంటే ఇప్పుడు టాక్ గురించి అడిగినప్పుడు అసలు నా నోట్స్లో ఏమున్నాయని పాతవి చూశాను. అసలు అప్పటికి నేను నేర్చుకున్న దానికి, ఇప్పుడు చెప్దాం అనుకున్న దానికి అసలు ఈ మాత్రం చెప్పాలన్నా అప్పుడు అసలు అబ్బో అనిపించేది. ఇప్పుడు వాళ్ళు బోర్డు అంత హెల్ప్ దొరుకుతుంది నాకు. సో ఇట్ ఇస్ యూ స్టార్ట్ విత్ ఎనీ ప్లాట్ఫామ్ లైక్ దిస్, IBM ఆర్ Penny ఆర్ గూగుల్ కూడా లర్నింగ్ ప్లాట్ఫామ్స్ ఇచ్చింది. యూ కెన్ స్టార్ట్ విత్ దీస్ థింగ్స్ అండ్ యూ కెన్ స్టార్ట్ యువర్ జర్నీ. బట్ ఏది స్టార్ట్ చేసినా ఫస్ట్లో కొంచెం వరకు, ఫస్ట్లో అంత కేక్ వాకలో చక్కగా మంచి సినిమాగా ఉంటుంది. మధ్యలోకి వెళ్ళిన తర్వాత మ్యాట్రిక్స్, పెద్ద మ్యాట్రిక్స్లు పెట్టి, హెర్మిషన్ మ్యాట్రిక్స్లు పెట్టి, ఇన్వర్షన్ ఉంటాడు, కాంప్లెక్స్ కాంజుగేట్ ఉంటాడు. అక్కడికి వచ్చేసరికి మనకి రియల్గా చెప్తున్నాను మైండ్ బ్లాక్ అర్థం కాదు. See, when I am saying with one qubit work బాగా, 2 qubits work బాగా ఉంటుంది మ్యాథమెటిక్స్. 4 qubits దగ్గర నుంచే కష్టంగా ఉంటుంది మనకి. 5 qubits దాటి దగ్గర నుంచి ఈక్వేషన్, ఇంటరాక్షన్ బిట్వీన్ దీస్ థింగ్స్ అంటే ఒక 5x5 ఇంటూ 5 డైమెన్షనల్ మ్యాట్రిక్స్ మనం తీసుకోవాలి. వాటిలో కంప్యూటేషన్ జరగాలి. ఇంటరాక్షన్స్, ఎవ్రీ స్టేట్లో ఇంటరాక్షన్, ఎవ్రీ స్టేట్లో ఆ ఇంటరాక్షన్ తో వచ్చే 5 స్టేట్స్ తీసుకోవాలి. అదొకటి. మనకి మ్యాట్రిక్స్ ఆల్జీబ్రా కనుక బాగా లీనియర్ ఆల్జీబ్రా, బేసిక్గా లీనియర్ ఆల్జీబ్రా అది అర్థమైతే, మ్యాథమెటిక్స్ స్ట్రాంగ్ గా ఉంటే మనకి ఈజీగానే ఉంటుంది. బట్ ఆఫ్ కోర్స్ మోస్ట్ ఆఫ్ దోస్ మ్యాథమెటికల్ టాస్క్స్ ఆర్ కంప్లీటెడ్ బై దీస్ థింగ్స్ అండ్ ద ఫైనల్ రిజల్ట్స్ దే ఆర్ గివింగ్. అది రిజల్ట్స్ వస్తుంటే వాళ్ళని నమ్మటమే తప్ప ప్రస్తుతానికి. See, if I am saying like I am putting my machine learning task on a IBM quantum machine, they gave some application. ఈ మ్యాట్రిక్స్ మల్టిప్లై చేసిన తర్వాత నాకు వచ్చే మ్యాట్రిక్స్, కాంప్లెక్స్ మ్యాట్రిక్స్, సే 10x10 మ్యాట్రిక్స్, 10 డైమెన్షనల్ మ్యాట్రిక్స్ నేను వాడికి ఇచ్చి దీన్ని 2 మల్టిప్లికేషన్ చేసి నాకు ఏమంటే వాడికి మల్టిప్లై చేసి రిజల్ట్ ఇస్తే నేను తీసుకోవడం. అండ్ దీంట్లో ఇంకోటి అనదర్ వన్ మోర్ ఫ్యాసినేటింగ్ అప్లికేషన్ ఏంటంటే, మ్యాట్రిక్స్ కింద వస్తే సైమిల్టేనియస్ సొల్యూషన్ ఆఫ్ ఎన్ ఈక్వేషన్. ఒక ఈక్వేషన్కి సొల్యూషన్ కావాలనుకోండి సైమిల్టేనియస్. ఫర్ ఎగ్జాంపుల్ దెర్ ఆర్ 10 వేరియబుల్స్. 10 వేరియబుల్స్ ఉన్న ఈక్వేషన్ తీసుకుని నాకు 10 వేరియబుల్స్ సాల్వ్ చేయాలంటే మనకు నార్మల్గా 10x10 మ్యాట్రిక్స్ కట్టి దానికి చేయాలంటే అది ఇది నాట్ easy task with the normal computer even today. But with quantum computer it can be done in a single shot with single process. And results ప్రస్తుతానికి అయితే మ్యాథమెటిక్స్ లో నేను ఇంకా అంత స్ట్రాంగ్ కాదు, అంటే నేను స్ట్రాంగ్ కాలేదు, నాకు అర్థం కాలేదు, కొన్ని చోట్ల నాకు అర్థం కాలేదు. అంటే బేసిక్ మ్యాథమెటిక్స్, బేసిక్ క్వాంటమ్ కంప్యూటింగ్ ప్రిన్సిపల్స్ ఇవన్నీ మనకి అర్థమైనప్పటికీ అది అప్పుడు బాగానే ఉంటుంది. ఆ కాంప్లెక్స్ మ్యాథమెటిక్స్ మనం చెయ్యం, అవి కూడా మనం క్లాసికల్ కంప్యూటర్ ద్వారా కంప్యూట్ చేసుకోవాలి. వాళ్ళు ఇచ్చిన రిజల్ట్స్నే మనం చూసుకుంటాం.
Actually, sir, in Python, there are which set of libraries are there
Oh.
deal with the matrices. So we have a concept called arrays. So in dimensional arrays also Python can deal with this.
అదే పైథాన్ లైబ్రరీస్ కూడా క్వాంటమ్ కంప్యూటర్ ఇచ్చి ఆ రిజల్ట్స్ తీసుకునే సాల్వ్ చేస్తుంది. పైథాన్ లైబ్రరీస్ కూడా లిమిటేషన్ ఉన్నాయి, అది కూడా కంప్యూట్ చేయాలంటే నార్మల్ క్లాసికల్ కంప్యూటర్ కాదు, క్లాసికల్ కంప్యూటర్ కూడా కంప్యూట్ చేయలేనివి క్వాంటమ్ కంప్యూటర్ ద్వారా మనం చేస్తాం. దట్ ఇస్ హౌ వి ఆర్ ఏబుల్.
Data in quantum computing. How to represent data in quantum computing?
How to
Represent in memory.
give our normal data onto the classical machine.
Yes.
అది క్వాంటమ్ మిషన్.
Yes. The representation means in memory.
మెమరీ అనేది క్వాంటమ్ కంప్యూటర్ ఉండదు.
No.
There are three different ways to give encoding technique, data encoding technique. Normal classical data, quantum computing. There are three different types of data encoding: amplitude encoding, angle encoding, bit encoding. మూడు రకాల ఎన్కోడింగ్ టెక్నిక్స్ మనం డేటాని అది కూడా ఎలా ఎన్కోడ్ చేస్తామనేది నిజంగా లోపల ఎట్లా ఎన్కోడ్ అవుతుందో తెలియదు. వాడు ఏపీఐ ఇస్తాడు, ఆ ఏపీఐ తోటి మనం ఈ డేటాని ఆ ఫంక్షన్కి ఇస్తే ఆ ఫంక్షన్ క్వాంటమ్ కంప్యూటర్కి ఈ డేటాని ఈ క్యూబిట్కి అసైన్ చేశానని చెప్పి వాడు చెప్తాడు, మనం వాడుకుంటాం.
Bob Elias for example చెప్పారు.
సార్ ఎక్స్క్యూజ్ సార్, మా డౌట్స్ ఏం లేని వాళ్ళు ప్లస్ ఆఫ్టర్నూన్ సెషన్ క్లాస్ ఉన్న వాళ్ళు యూ కెన్ లీవ్. ఇక రిమైనింగ్ వాళ్ళు ఇంటరాక్ట్ అయ్యే వాళ్ళు ఉండి
ఇంటరాక్ట్ అవ్వాలనుకున్న
ఉండండి. క్లాసెస్ ఉన్న వాళ్ళు వెళ్ళండి ప్లీజ్. లంచ్ ఈస్ ప్రొవైడింగ్ అట్ క్యాంటీన్, తీసుకొని వెళ్ళండి.
Bob send చేశాడు, encryption చేశాడు, Elias receive చేసుకున్నాడు. Elias also forget what you put sir.
ఫర్గెట్ ఫర్గెట్ ఏది
Okay.
Forget.
Data collapse అయిపోతుంది.
ఈ రిసల్ట్ చేసిన డేటా రాదా? మన తాళం పోయింది అనుకోండి, మనం ఓపెన్ చేయలేం కదా. అట్లాగే
There is no probability. There is no probability in quantum computing.
అది రికవరీ చేయడం
Yes, many chances అనేది లేదు ఇంకా అయితే. అంటే ప్రాబబిలిటీ ఛాన్సెస్ లేదు. ఒక కీతో ఫస్ట్ టైం చూసి సెకండ్ కీతో సెకండ్ టైం థర్డ్ కీతో థర్డ్, దేర్ ఇస్ నో ఛాన్స్. డేటా క్రాష్, ఎంటైర్ డేటా క్రాష్.
ఈ మధ్యలో ఎవరైనా ముట్టుకున్నా కానీ ఫర్ ఎగ్జాంపుల్ చిన్న లాజిక్, శివుడు పార్వతి దేవుడు ఇద్దరు మాట్లాడుకుంటారు, ఇంకోటి ఎవరో నాలుగు వెళ్ళి విందామని ట్రై చేశారు, ఫినిష్ మటాష్ నాలుగు
అంటే రిసీవర్ కూడా అది మర్చిపోయాడు. రిసీవర్ కూడా ఫర్గాట్.
అసలు ఫర్గాట్ అంటే లేదు లేదు లేదు
వాట్ ఇన్ బాక్స్
సెక్యూరిటీ కదే కదా. నేను మీకు తాళం ఇచ్చాను, తాళం లేదంటే మీరు ఆదరణ సెట్ అవుతారు, వేరే మీకు ఆల్టర్నేటివ్ లేదు.
సార్ ప్రెసెంట్ ఇప్పుడు ఉన్న మన ఎడ్యుకేషన్ అకాడమిక్ సిస్టంలో అయితే క్వాంటమ్ కంప్యూటర్ యొక్క నెసెసిటీ లేదు, అంటే అంత యూజ్ అప్లికేషన్ లేదు
ఇప్పటికి లేదు.
R&Dలో కానీ ఫ్యూచర్ R&Dలో
ఫ్యూచర్ అంటే ఆర్ఎండ్లో కానీ యాక్చువల్గా చెప్పాలి అంటే ఈ IBM వాళ్ళు, గూగుల్ వాళ్ళు వీళ్ళంతా ఇన్వెస్ట్ చేసి ఎక్కువ మంది వాడుకుంటే కానీ
అది ఇంకా దాని బయట కాదు.
వాటి యూసేజ్ ఉండదు.
అవును,
దాని మీద హైప్ తీసుకొచ్చారు మార్కెట్, హైప్ ఉంది కాబట్టి అంటే కాంప్లెక్స్ ప్రాబ్లమ్ సాల్వ్ చేయగలదుగా. తయారు చేశారు మిషన్, ఎలా వాడుకోవాలి వాళ్ళకి తెలియదు.
అంటే ప్రజెంట్ ప్రతి స్టూడెంట్ ఇప్పుడు కంపల్సరీ క్వాంటమ్ అనేటువంటిది
అంటే నెక్స్ట్ వచ్చే జనరేషన్ 20 ఏళ్ళ నాడు ఎలక్ట్రానిక్స్ చదువుతున్నాము అంటే మనకి మినిమం హాకీస్ ఇస్తే అప్పుడు అదే చదువుకుంటున్నారు అనుకుంటుంది. ఇవాళ మినిమం హాకీస్ లేదు, అసలు ఆ టెక్స్ట్ బుక్ చూడలేదు. ఇవాళ క్వాంటంలో అలా ఉన్నాం, స్టార్టింగ్ లో ఉన్నాం. రేపు పొద్దున వీళ్ళందరూ వాడితే అది నెక్స్ట్ స్టేజ్కి వెళ్తుంది.